Hi everyone, welcome back to Made Everything Official. Cold hammer forging is a process of strength and precision. A steel blank is placed into a forging machine where massive hammers strike it repeatedly around a mandrel. Each blow compresses the metal, shaping the bore while strengthening the grain structure. In just moments, the rough blank transforms into a hardened barrel, with accuracy and durability forged directly into its core. This method ensures consistency, longevity, and performance, trusted by experts worldwide. Automation takes center stage here, with an integrated gantry robot loader feeding parts directly into the CNC lathe. This seamless system ensures continuous operation and eliminates unnecessary downtime. The material being machined is 303 stainless steel, a durable alloy known for both corrosion resistance and strength. In this demonstration, the entire cycle is completed in just over 5 minutes, using 23 different tools to perform a wide variety of operations. At the heart of the machine are CNC Lathe tool holders, capable of reaching speeds up to 12,000 revolutions per minute. These high-performance tools allow not only standard turning, but also complex milling and drilling tasks within the same setup. Next, the Y-axis capability enables parting off with exceptional accuracy. This additional axis of movement gives the operator more freedom, ensuring that the final separation of the part is smooth and precise. Angular drilling demonstrates the machine's ability to reach geometries that would otherwise require multiple operations. With precision control, holes are cut cleanly at exact angles, expanding design flexibility. Altogether, the TTL series CNC Lathe shows how automation, high-speed live tools, and multi-axis control combine into a powerful machining solution. Each feature works in harmony to reduce cycle times, increase accuracy, and deliver reliable results for complex stainless steel components. This is where CNC machining comes into play. Starting from a solid block of high-strength alloy, advanced 5-axis CNC machines carve out the shape of a turbine blade with micrometer precision. Every cut, every contour is executed with programmed accuracy, ensuring the blade matches the exact design specifications. After machining, finishing processes such as polishing and surface treatments are applied, giving the blade durability and flawless performance. Each turbine blade is not just a piece of metal. It is a finely engineered component, shaped to capture high-energy airflow with maximum efficiency, forming the beating heart of a jet engine. Behind this precision lies the drive for safety and performance in aviation. Each blade must withstand extreme temperatures, intense pressures, and countless cycles of stress, making flawless production an absolute necessity. This is the Kurt Max-Lock HP 5-axis Vise in action, a precision work-holding solution designed for advanced machining operations. At its core is self-centering capability. The Vise aligns parts automatically, reducing setup time and ensuring consistent centering across batches. Serrated or dovetail jaws grip securely, while Kurt's Ang-Lock technology counters lift and maintains clamping force even under heavy cutting loads. Designed for high rigidity, the Max-Lock HP achieves repeatability within plus or minus 0.0005, keeping parts stable even during aggressive machining. Its robust body and hardened components reduce vibration and deflection, essential when working with tight tolerances. In a 5-axis setup, this vise supports complex toolpaths and multi-directional cutting. Whether you're performing simultaneous operations or intricate angled cuts, the workpiece stays rooted, enabling precision from every angle. Automation is seamless. The vise integrates easily into robotic or gantry systems, making it well-suited for high-volume production environments. Its design allows for quick reconfiguration, supporting both ID and OD clamping with minimal changeover. From the very beginning, the journey of a medical screw starts with premium-grade titanium, a material chosen for its biocompatibility, strength, and lightweight properties. This ensures the implant can endure stress inside the human body, while integrating safely without risk of rejection. Next, the raw titanium rods are placed into advanced CNC machines, where micron-level precision transforms them into life-saving components. Every cut, every thread, and every contour is shaped with surgical accuracy. Multi-axis machining allows threads to be formed smooth, sharp, and consistent, guaranteeing stability once implanted. To achieve flawless performance, the machining process is followed by polishing and surface treatments. These steps enhance durability, prevent wear, and ensure that each screw meets the exact standards required in medical surgery. The barrel's story begins with solid steel, carefully selected for strength and consistency. Each blank is prepared and centered, ready for the intense shaping that follows. Cold or hot forging compresses the metal, aligning grain structure and forming the initial profile. This forging step builds the barrel's fundamental strength, creating a foundation that machining will refine. Next, the blank is bored and reamed to establish a precise bore. Cutting tools remove material with controlled passes, bringing the internal diameter to exact specification before rifling is applied. Rifling then carves the spiral grooves that stabilize a projectile in flight. Whether formed by broaching, button rifling, or hammer forging, these grooves are cut to tight tolerances, each twist and depth carefully controlled to ensure consistent accuracy. After rifling, barrels undergo honing and contouring to perfect the bore finish and external geometry. Surface treatments and heat cycles may follow to optimize hardness and wear resistance. Finally, each barrel is tested. Chamber checks, headspace verification, and proof or accuracy tests confirm performance under real conditions. The creation of the Ruger GP100 registered begins with carefully forged steel frames, each one designed to withstand decades of use. As the raw blanks enter the machining floor, precision becomes the guiding principle. State-of-the-art CNC machines carve every contour of the revolver's frame. Multi-axis tools remove material with micrometer accuracy, cutting the complex geometry needed for strength, ergonomics, and function. Barrel seats, cylinder windows, and lockwork pockets are shaped with exacting precision. Every drilled hole, threaded bore, and milled channel is positioned to tolerances that guarantee a perfect fit once assembled. The cylinder is then machined from a solid block of steel. Each chamber is bored and reamed to ensure consistent dimensions, while indexing cuts establish flawless rotation and timing. Ruger's process ensures that each round locks into place with uncompromising reliability. Additional machining prepares the trigger guard, hammer, and small components. These parts undergo the same careful milling, drilling, and contouring, so that every piece integrates seamlessly into the revolver's mechanism. Throughout the process, constant inspections verify accuracy at every stage. By combining advanced automation with hands-on quality checks, Ruger ensures that the GP100 registered is not just manufactured, but truly engineered for durability, accuracy, and safety. What begins as simple steel is transformed into one of the most trusted double-action revolvers in the world, the Ruger GP100 registered. In the world of precision manufacturing, stable work holding is just as important as the cutting tools themselves. The Kurt-Schenke clamping system was developed specifically to meet the demands of advanced 5-axis machining, where absolute rigidity and unobstructed access are critical. At the start of the process, the compact design of the clamping unit secures the workpiece firmly while minimizing interference with the toolpath. This allows cutting tools to reach all 5 sides of the component without the need for constant repositioning. The result is improved accuracy, higher efficiency, and reduced cycle times. Crafted from hardened steel and engineered for repeatability, the clamping jaws deliver a grip that withstands the immense cutting forces of high-speed machining. Whether holding raw stock or finished precision parts, the system ensures consistent pressure, preventing vibration or micro-movement that could compromise surface quality. Its modular design makes it adaptable to a wide range of applications, from aerospace components to medical implants. By providing stable fixturing across complex geometries, the clamping system allows machinists to take full advantage of modern multi-axis CNC machines. Every detail, from quick-change inserts to high-strength fasteners, is built to streamline operations and extend tool life. The result is a solution that combines durability with productivity, giving manufacturers confidence in their machining process. With the Kurt-Schenke clamping system, precision is locked in place, ensuring that even the most complex parts can be machined to exact specifications, efficiently, reliably, and with world-class accuracy. The journey of forging a hammer begins with raw material carefully selected for both strength and durability. Here we start with a block of 1045 carbon steel, measuring 3 inches by 1.75 inches, weighing just over 2 pounds. It may look unremarkable now, but within this billet lies the potential to become a tool that will serve a craftsman for years. The billet is first heated inside the forge until it glows a vivid orange. At this temperature, the steel is no longer brittle but plastic, ready to be shaped by tremendous force. This is where the 24-ton hydraulic forging press comes into action. Unlike traditional hand hammering, this immense press can move metal with precision and efficiency, forcing the steel into shape with each controlled stroke. The first stage is drawing out the billet, compressing and elongating the metal so its mass is distributed properly. One side begins to take on the shape of the hammer's peen, while the opposite side is prepared for the striking faces. Each press not only shapes but also refines the internal grain structure, aligning the steel's crystalline makeup to make the finished hammer tougher and more resilient. After the initial shaping, the steel is reheated. Forging is never a single step. The billet must repeatedly return to the forge, ensuring it stays at the right temperature. Too cold, and the steel may crack under pressure. Too hot, and the surface may burn away precious carbon. Skilled timing ensures every strike from the 24-ton press achieves the perfect balance. With the rough shape established, the focus turns to creating the hammer's eye, the critical opening where the wooden handle will fit. A punch is driven through the glowing billet, and with careful drifting, the hole is opened and aligned. The forging press makes this process far more controlled than hammering alone, ensuring the eye is centered and precise. A well-formed eye is vital, as it guarantees stability and safety once the handle is mounted. Once the eye is formed, the head is pressed and shaped further. The flat striking face is squared and leveled, while the opposite side is crowned into a smooth, rounding face. Each reheat allows for additional refinement, gradually transforming the billet into a balanced hammerhead. The symmetry and proportions are carefully checked, since even small errors would affect how the hammer feels in the smith's hand. After forging is complete, the hammerhead undergoes normalization. It is reheated and then allowed to cool slowly, relieving internal stresses built up during pressing. This critical step evens out the grain structure, preparing the steel for the next stage, grinding and heat treatment. On the grinder, excess scale and material are removed. The cheeks are smoothed, the eye is trued, and the striking faces are shaped to exact geometry. Grinding is not just about appearance. It ensures the hammer delivers force evenly and safely. At this stage, the hammer begins to resemble the final tool, but its mechanical properties are not yet ready for work. Heat treatment follows. The hammerhead is reheated to a controlled temperature, then quenched rapidly in oil. This hardens the steel, locking in strength so the faces will withstand countless strikes. However, hardness alone makes steel brittle, so tempering is applied next. By reheating to a lower temperature and cooling again, the metal achieves the ideal balance of hardness and toughness. Now the hammer can resist chipping while maintaining durability through years of use. Finally, the wooden handle is fitted. A hickory or ash handle is shaped to slide tightly through the forged eye, then wedged to lock it in place. This marriage of wood and steel completes the transformation. The handle provides shock absorption and control, while the forged head delivers power and precision. The result is a rounding hammer born from fire, force, and skill. Every stage, from heating, pressing, punching, grinding, to tempering, contributes to its strength and reliability. What began as a plain block of carbon steel has become a craftsman's trusted tool, forged under 24 tons of pressure and refined with centuries of blacksmithing tradition, enhanced by modern technology. Today, let's step inside the factory to uncover the secrets behind how golf balls are made. Each ball begins with advanced materials. The core crafted from synthetic rubber or polymer compounds, engineered to maximize energy transfer and control. The outer cover, made of ionomer or urethane, is chosen for durability, spin, and feel. Even the smallest material choice can change distance, accuracy, and overall performance. The core is molded under intense heat and pressure, giving the ball its rebound, compression, and responsiveness. Modern factories use precision molding techniques to guarantee uniform density and perfect roundness. Many premium designs even feature multiple layers, where a mantle wraps the core to fine-tune spin and control. Next, the cover is formed, and the iconic dimple pattern is pressed into the surface. Far more than decoration, these dimples are carefully engineered to optimize aerodynamics, creating lift and reducing drag for the ideal flight path. Before leaving the factory, every ball is tested for weight, roundness, compression, and spin. Only those that pass strict quality control move forward to painting, logo printing, and UV-cured finishing. The result is a flawless ball built for performance, ready to take on the course.